So our work is motor imaginary brain activity recognition through the data augmentation using the DC-GANs and mu sigma. So the BCI is a component computer-based system that acquires brain signal, analyze them, and translate them into components that make the external device carry out to do the desired action. So the BCI is like the collaborator between the human and the computer. And by doing the translating the human brain signal, we can translate it and send this information to the computer. Then that signal can control the cursor or the robotic, for example, hand or leg. So in most of the BCI study, EEG signal have been used to analyze the brain activity, which are recorded using a number of electrodes and have high temporal resolution. One approach to record the brain activity is to use the EEG cap with the multiple electrodes on it. And EEG measure the electrical activity of the brain. Then if we use that signal, then we are able to communicate that through the computer. So the most important application of the BCI system is in the neurohabilitation application that make it possible to get a good and promising result for rehabilitation purposes. So the idea of using the brain-computer interface for rehabilitation, so this make it possible to translate this in information and couple it with the robotic hand or for rehabilitation purposes. So the application of that is very promising for the healthcare system, but it is not the only application of this brain-computer interface. We can use that also for gaming system. So for the VI game system, we can use this event-related potential signal to capture the brain responses to the simulator, which allow for an intention-based interaction. Other than that, we can use that for in the brain sensing headbands that can be used to monitor the brain activity, to measure the states of the focus, relaxation, or the mind wandering as a part of the meditation practice or cognitive training program. Having said that, all the importance of the processing the brain motor task imagery in the brain-computer interface, our motivation for this specific paper is to tackle the problem of having access to a limited data set, and how we, by the advantage of generative method or the mu sigma method, we can do the data augmentation. But let's talk about briefly that how we pre-process this kind of data. So for the pre-processing the data, we use the common special pattern technique that we have proposed a modified version of this CSV-based method to pre-process the EEG signal. And the CSV algorithm calculates the special filter that maximize the ratio of the variance of the data from the two classes. So the whole motivation is coming up with the special filtering that is able to create the difference between the two classes. And it will do that through by maximizing the variance of the one class while simultaneously doing the minimizing the variance of the other class. And some researchers continue using the complete CSV-based method, but here in this work, instead of doing the final stage that finding the logarithm variance, at the end to distinguish between the two clans, we stop at that stage and just extract the two-dimensional signal that has both feature information in the time and the frequency domain. And from that, we create something similar to the image. Then what we try to do is to apply some classification technique that has been done on the image signal. So the data set that we use for these experiments, we use the EEG signal data taken from the PCI competition tree. So these are the information about this specific data set that contains the 5 subjects, and for each of these subjects, we have access to the number of training and the test data set. But as you see that the amount of data we have for each of those subjects are limited. So the pre-processing approach that we have for the signal, at the first we using the bandpass filtering of using the fifth order Butterworth filter in the range of the 7 to 30 hertz. Then the filter EEG signal is smoothened by the whitened moving average filter in the window size of the 10 sample at the time. Then we apply the CSV method that I explained in the previous slide. Then after the amount of the dimension of the signal we have is 201 by 6 dimension sample. Now the problem we have with dealing with this EEG signal is that it is the low signal to noise ratio signal and is also non-stationary characteristic. And also the amount of data that we have access as label is limited. So some pre-existing work is available to address the first two challenges that exist in the processing the EEG signal. But here in this work, we are targeting how we can handle the low amount of the data as at our training stage. So here in this work, we are using 2 techniques to handle that with the DC-GANs and the mu sigma. In the following slide, I explain a little bit each of those terms. So first of all, the DC-GANs is a deep convolutional GANs method used for data augmentation. So for the ones that are not familiar with that, is model include the generative model that generate augmented data set as well as real data set, which are both pass through the discriminator and which further create a generator loss and a discriminator loss. So through the training, what this method is trying to do is try to maximize the discriminator loss, at the same time minimize the generative loss in order to generate the augmented sample that is more similar to our training data set. So this is the result we got after doing the data augmentation using the DC-GANs. So this is the TSNE visualization of the data for the case that we don't apply augmentation, and this is the result after applying the GANs method. So I'm sorry. Both of them are the result for the GANs method, but for this one is the right hand and the other one is the right foot. Then at the next step, we also try another way of doing the data augmentation. We use the mu sigma method. So the way that this technique works is create the random noise signal with the mean of 0 and the variance of the coming from the variance of the individual input signal data set. Then we add it and subtract this noise from the original signal. And using that, we create another data augmentation. Then we apply the different deep learning approaches, and we want to investigate that why these 2 means of the data augmentation, if we are able to improve the result of classification or not. And this is the result of data augmentation using the mu sigma method, again, for both the right hand and the right foot. So the deep learning approaches that we use here is we use the MLP method. The specification for that network is using the 3 hidden layers with 200, 150 neurons in each layer, respectively, and use the relo activation in the first stage. And as an output layer is the signal. For CNN-based, it used the two convolutional network block with the batch normalization and the 4x4 filter followed by max filling. And at the end, we have the fully connected layer of the 10 nodes, and again, the sigmoid is the final layer. Then we also investigate if we apply the RNN method, this applied to the RNN layer of with the 28 and 12 neurons, followed by two dense layer of the 16 and 10 nodes. And the last one is if we use the LSTM. And these are the specification if we goes with the LSTM model. In the following slide, we study the result. For the case that there is no augmentation happen for the MLP, this is for the case that we do the augmentation of the mu sigma. The next column is result for the GANs. So the way that they study and evaluate the performance is based on each subject. So having the subject AA, AL, AV, AW, and AY. And the result is shown in bold for each of those methods, for MLP, CNN. So as you can see that when we apply the data augmentation for the GANs method on the MLP, is improve the result for all the subjects except for the AV, but it still is having a pretty good result. For the CNN-based method, is also good, having a good result, but not necessarily is always improve the result using this type of augmentation. Then the next slide, we also do this same experiment using the RNN and LSTM method. Here, for when we apply the RNN method for the classification, the mu sigma, the way of augmentation, give us a better result. But for the LSTM, the GANs method is still help us to improve the result. So these are just a comparison between those techniques. After that, we try to compare it with the pre-existing work, and we see that where are in the competition for this on this data set. So in this slide, we show the result and compare it with some of the state of the art in this area. But for ARCID, we just use the best result we achieve among all these methods. So the best result we achieve is using the MLP and also combination with the data augmentation with the GANs. And the good thing about that, so most of the technique, maybe they are performing well on one subject, but they are not keeping the same result over all the subjects. Versus this one, that after the data augmentation, we are getting the pretty good result of all the subjects, the 5 subjects that we have on this data set. So what we try to show that for this specific EEG signal processing, that creating the label data is not easy task, and all the people have this difficulty when they have access only to limited data set. That however, by applying the data augmentation method, how you can improve the result and getting the promising result on all the subject. Not your method is only work on the few subject. And these are some references. And thank you for your attention.